Okay, so let's start the next session. This session is about collision detection and avoidance and also sensing. The way the session's going to work, just to remind everybody, is there'll be a 20-minute keynote talk first, and then each speaker will have 3 minutes to give a short presentation of their work. The odd-numbered speakers should be on the left-hand side from the audience point of view over this side, and the even-number speakers should be here and talk here. So you'll have 3 minutes to set up your presentation on the other side from the current speaker, and so please come up straight away and set it up, and then you'll have 3 minutes to talk, and you'll be cut off after 3 minutes, so please make sure you're going to finish within the 3 minutes time. So I'd like to introduce our keynote presentation, which will be given by Christian Laugier, and the presentation's about Bayesian perception and decision from theory to real-world applications. Is Christian here? It's a pleasure to introduce Christian Laugier to give our keynote presentation. Thank you.
So thanks so much. Good morning, everybody. As the talk address today a topic which is large and important. It's basically the idea is to have safe and socially compliant robot navigation, but in open and dynamic human environment. But it's too large, and I will focus on 2 points, the perception and the decision. And this using Bayesian approaches. So I will also focus more onto one of the applications, which is autonomous vehicle. So the main features of this problem to be addressed is the first one is about the fact that the world is dynamic and open. So we have to take care of this when designing the models. The second point is linked to this one, so it's incompleteness, and also we have to manage uncertainty. And uncertainty at both the model and the perception levels. And finally, one thing also which is important is that human is in a loop. So we have to address some social and interaction constraints when making the decisions. For the first point is about perception. So we need to have robust perception for this kind of dynamic human environment and processing different level of perception. The first one is basic level for sensor fusion, SLAM, DATMO. The second one take into account some contextual information and also semantics in order to make interpretation. And the last level is close to the application. For vehicle, the idea is to detect what is a safe navigable space at a given time. So the main difficulty, again, is the fact that you have to process noisy data, incompleteness, dynamicity, and this is about discrete measurement from the system, and of course in real time. So all the model and the algorithm have to take into account this important constraint. So the approach, what we call Bayesian perception, introduce 3 main levels. The first one is about the reasoning. The reasoning has to be done, of course, about uncertainty, but also using a time window, because we have to take into account past events and also the near future, and make a prediction for what will be probably the near future. And decisions depend on this. Second point is about the improvement, so that means the robustness. And for this, we are making Bayesian sensor fusion of different sensing technologies using Bayesian inference. And finally, the interpretation of the scene using the semantic and contextual information. The second challenge is about human-aware decision-making for both navigation and interaction. So the difficulty here is that we have to take into account 2 things. The first one is the context, And sometimes, for instance, if you look at the situation where there is traffic congestion, it's clear that a human being is unbeatable in taking the right decision. Then this means it has to cooperate with the vehicle. In other cases, the system needs a fast answer of the system. And in this case, for fast control, probably the computer is better. So the main difficulty, again, is about the uncertainty, the fact that we have to deal with partial knowledge, and also the world is constantly changing. And again, human is in a loop. And again, we have to do this in real time, taking the decision at the right moment. So the approach for this is to combine prediction. So we need to envisage what will be in the next step in a few seconds, the risk assessment depending on this, and the Bayesian decision taking into account the uncertainty. So of course, we needed to avoid collision. We need to avoid pending collision, but also we need to avoid future collisions, because it depends also on the current state, if the collision will be possibly avoided or not. And for this, we are computing the probabilistic collision risk at a given time, which is t current time plus an horizon delta. And decision-making also has to take into account all the other participants around the vehicle. So let me move to the first technology, Bayesian perception for a dynamic environment. The idea is to use a representation based on the grid, on the probabilistic grid, the P grids. But since we are dealing with a dynamic environment, we have to combine two things. The first thing, which is based to the occupancy, probability of occupancy, so I mean this is the space, but also the velocity. And we need to have distribution of the velocities in order to have this dimension into the model, because the decision has to take into account both information. So for this, we have designed an approach which is basically using P grids, probability grids, and with Bayesian filtering, which operate at 25 Hertz, at the same rate than the sensors, with a classical prediction and estimation model. And then the information is into the grid, both for the occupation and both for the histogram of velocity, which is predicted by the system. The approach has also been developed in order to be highly parallel processing, because one of the goals is to implement this on the specialized hardware, like, for instance, first implementation in GPU, but also multi-core architecture or system on chip. One important property of this approach is to have the conservative prediction capability inside of the inference system. So this means that it's possible to apply this in order to execute collision avoidance or collision anticipation using only this information. Like, for instance, you have here an example of a pedestrian is here, is probably going to the street and cross the street. So this is an autonomous vehicle. This is the vehicle which is parked. At one point, this guy is detecting and tracking the pedestrian. At one point, he will not see anymore the pedestrian, but you will see that he will stop, because it will make the prediction that probably the pedestrian will continue to move. And this is completely embedded into the process. But we still have some problems with the accuracy of the computation of the velocities and the required size of the memory. So we have improved this recently by making an hybrid system and by separating what is static by what is dynamic. And the static part is represented traditionally using occupancy grid, and a dynamic part is represented using a set of particles. It's a kind of a vector field of velocities. And it's really more accurate, since Moreover, we can use the information coming from the sensor inside of the car in order to update the model. So in this case, we have two parts, the static part, the static component, which is represented using occupancy grid, and the dynamic component, which is represented by these sets of particles, which allows smooth integration of the motion of the vehicle in order to have really better results in terms of the reality of the solution. Then all the information is propagated into the grid, and the set of particles are moving into the grid according to the dynamic model, of course, included into these particles. So this is an example. So I stop here. No, it doesn't work. Okay, so this is an example in downtown Grenoble. So our car is here, so this is another car. There's a lot of pedestrians in downtown city, and we are moving into the city. And what you can see here is the result of the scanning using the laser, the result of the construction of the occupancy grid, and the result here of the tracking, the detection in real time of what is moving and what kind of velocity of the guy who is moving. So this is, for instance, this car. Each pedestrian are easily recognized and detected using the approach. So I will come back to this for later for the detection of the risk. So this has been implemented onto this car, Lexus, with cooperation with Toyota. Based on, at the moment, we have two laser scanner and a stereo camera, not also a camera here. So this is the implementation inside of the car, and what we are currently doing is to miniaturize the system by implementing it onto a GPU, a new GPU NVIDIA, from NVIDIA, but also we made an implementation onto a mini-core storm architecture in order to reduce the size, reduce the energy consumption of the system, and improve the efficiency of the system. So basically, this is the thing we are obtaining using directly the information processed by the system. So I mean recorded trajectory using OpenStreetMap, GPS, EMU, and so on. This is a result of the sensor fusion, and this is a result of the analysis of the situation, which give at each time step what is the navigable space just in front of the vehicle. So this architecture is then combined with a model in order to construct object, to detect object, and to track object, and to understand what objects are doing. Object can be bicycle, can be pedestrian, can be cars, and so on. So without going into the detail, what is the output of this kind of system is all these things. So I mean, this is a laser fusion, this is a result of stereo vision processing, this is a result of object classification, this is a result of the motion detection, and this is a result of the tracking of the lane in order to localize the vehicle onto a given lane. Just a couple of videos just showing the system, how it works. So this is the processing using a stereo vision system, where we can see here, this is the road. And in red, we have static obstacles and also the dynamic obstacles. And this is the result of the Bayesian sensor fusion, including stereo vision, including laser scanners, and the result is not really visible for anybody here, but basically the result is the fusion of this information into this model, again combining occupancy probability and velocity probabilities. Now the next step is how to use this information in order to make decisions. And for this, we have to, again, make an assessment of the situation and an assessment of the risk and making then the right decision. The first level of decision for collision prediction is to use the basic processing, so I mean inference inside of the system. For instance, in this case, using the HS-BOF. So this is what we call estimation short-term collision risk. Then the objective is to estimate the collision risk at an horizon delta. Delta is about 1 or 2 seconds, that's all, very short. And we also needed to localize where the danger is. So we need to localize in space and in time. And this is done, of course, by the system. But at this level, we are not processing the object level. Again, it's at the basic level of system, inside of the embedded system, inside of the vehicle. We already have this additional information. Not only there is some object here, there is some object moving here, but we're adding now a risk value associated to this. So this is an example here. I will show you a video on this, where we are using a crash situation with this guy, and we are following this vehicle. I will show some result just after that, and where we can detect here the danger. So this can be connected with a system for warning the driver, but also this can connect it directly to a hard braking system. So for the approach, what we are doing, in fact, at each time step, we are projecting the estimated scene. So what is the current situation of the scene in terms of occupancy, in terms of velocity, velocity represented by particles, and we also project the car model, shape and velocity, onto the grid. So this is what is represented here. So this is a representation of the shape and the size of the car according to the size of the grid. So this is a static obstacle, this is a moving obstacle, where we have several particles representing the velocity. At the time step t+1, so these guys, I mean, the vehicle has moved onto this position. Then, of course, the static obstacle doesn't move, but the dynamic object has moved at the same time, and we have several particles here, here, and also here, which are presented into the grid. So this means at this point, we are a slow, not a slow, low risk of collision, because we have just a couple of particles just colliding into the model of the car. And at time t+2, the car also collides with the static obstacle, and the risk is higher. So the idea is to make the integration of the risk over the time range t, which time t plus the delta. Delta, again, is 1 or 2 seconds. So this is some experiments in downtown Grenoble. So this is in a urban street in Grenoble. And this is another situation where we make experiment on the crash scenario. Of course, of crash scenario, we are using a mobile puppet in order to make the experiments. As a result, we detected a few seconds ahead all risky situations encountered by the car. And for the validation of the real traffic data, for urban environment, of course, we didn't add collision, but we have no false alarm for car pedestrians using the system. For crash scenario, I will just show you just after this slide how it works. All the collision had been predicted before the crash, at about 1 second or 1.5 seconds before. So this is one example of the crash situation. This is the puppet. Our vehicle is here. We are following this white car, which is driven by a human driver. And at this point, you can see that our vehicle is here. We don't see the pattern here because it's not visible because of the car. But at the last moment, this car decided to avoid the puppet, And then we detect at this point that there is a puppet here, and this is an alarm which is given here approximately 1 second before the crash. But this is not enough because we have to reason in more complex situations, and also to reason at the object level. For instance, if you look at this situation at the intersection, so this car, we don't know at the moment if this car is going to go straight or turn left, so there is pedestrian here, and the question is he going to cross the road and so on. So we have to take care of all the participants here and to integrate this information in order to compute the level of risk. So this means that we have to understand the current situation and also its likely evolution, again, at the object level at the moment. So this can be used for evaluating the risk of collision and for making safe navigation decisions. So I will skip the detail of this, because it seems that the time is over. Just a video showing how the system is working on the road. In fact, this is the speed of the vehicle, it's about 100 kilometers per hour, the risk and the time to collision. On the different tracks, we can see the prediction of the truck is going to move straight or to turn left or to change on the right lane. And this is the representation of the risk for the driver of the vehicle. A last video in order to show how the system is working in case there is several participants in intersection, where in this case we need to have a different way to reason. In this case, we have to use a human-like reasoning process by comparing the driver intention and the driver expectation. And comparing both, then we can detect a possible risk. And this is a video showing how the system is working. And it's valid. Okay.
Okay, my name is Andrea Zanchettin. I'm going to present this work, which is titled Real-Time Collision Avoidance in Human-Robot Interaction based on Kinetostatic Danger Field, which has been developed in my lab in collaboration with Matteo Parigi, who's a former master student, and Professor Paolo Rocco. So we have been working in our lab in human-robot collaborations since quite a few years, so addressing different topics. One is injury quantification for physical interaction, ergonomics and comfort during the human-robot interaction, intuitive programming, and of course collision avoidance, which is going to be the main topic of my presentation. So there are many alternatives to cope with collision avoidance. One is, of course, randomized planning, based, for example, on RRTs. The other one is artificial potential field, and probably many, many others. But sometimes they are difficult to be adopted in real time, or they are poorly capable of capturing the geometry of both the obstacle and the robot. So we developed the so-called kinetostatic safety field, which is very convenient to be used in real time, so in closed form solution, so we can compute that quite fast. As you can see, it's something like 1 microsecond, and it is very capable of capturing the whole geometry of the robot and of the obstacles. So we use this, of course, with a control strategy, where we can use this field to avoid obstacles based on null space projection. And eventually, when the risk of collision is too high, we can relax the task in order to fully exploit all available degrees of freedom. So we did some experimental validation based on dual-arm ABB UMI robot, which you probably have seen at the IMTS fair. We used the Microsoft Kinect, and the reflexes motion library for trajectory generation. So here you can see some experiments from our lab. So you will see self-collision avoidance on the left and human-robot collision avoidance on the right. So the main features here is that the robot on the left is trying to maximize the distance between the two arms, so it's self-collision avoidance, and on the right you can see task relaxation. So that's it. If you are interested, just stop by to our interactive presentation. Thank you.
Good morning and welcome to my presentation. My name is Andreas Lawitsky. I'm with the Chair of Automatic Control Engineering at TUM in Munich, in Germany. This is some prior work of us with my student Anselm Niklas and my professors Dirk Wollherr and Martin Buss. And the topic of this work is determining states of inevitable collision using reachability analysis. Just a short motivation what we were trying to do. So think about that we have an autonomous platform which is driving towards a wall. And the most intuitive approach to guarantee safety here is to use your trajectory generator and check all your trajectories for a collision and just execute one which seems to be collision free. However, this might lead to situations where at a later time step, you will be, all your actions will end up in a collision. These are called inevitable collision states. So you engaged your brakes just too late. And of course, we need to determine and avoid such states beforehand, which is pretty straightforward, of course, for one-dimensional systems with static obstacles, but becomes really challenging for higher dimensional systems and dynamic obstacles. And there's different approaches to solve this problem, and what we're doing in this work is we are fusing the approach of inevitable collision states on the one hand and reachability analysis on the other hand. With this, we are able to determine all the states which will inevitably lead to a collision, and we can avoid them later on. With that, I want to thank you all for your attention, and I'm looking forward to meet you in the interactive session.
Hello everyone, my name is Zhonghua Xie, a PhD student at George Mason University. Today I'm going to present a paper called Collision Prediction Among Polygons with Arbitrary Shape and Unknown Motion. This is joint work with Yan Lu and our advisor Jimmy Lian. So why collision prediction is important? Since safety is a key issue for motion planning in dynamical environment with moving obstacles, usually human and animal robots, we want both of them to be safe. So some existing work proposed to model both robot and obstacles as disk and do conservative collision prediction based on the disk shape. However, think about a scenario that in disaster zones, airports, or warehouses, robot navigates itself among many other mobile robots or manipulators carrying cargoes with various shapes and sizes. If we model the obstacles as disk, you find it's impossible to find a collision-free path. So our main contribution is that we advance beyond the translational and the disk model, that we can predict collision for a point robot with polygonal articulated obstacles. This is done in our previous work. And in this paper, we particularly focus on the case that both robot and the obstacles are polygonal shape. And compared to a method that replan periodically without collision prediction, we show that our method provides a higher success rate while it can reduce the number of replans significantly. The key idea is to compute the earliest collision time for a robot moving on a path. Contrary to traditional motion planning, we not only plan a path for the robot to execute, but also plan motions for the obstacles. We model obstacles as adversarial agents, trying to minimize the time for the robot to remain safe on the path. So given time t, we know where the robot is, and the motion of an obstacle is calculated to minimize the time to hit the robot, and that can be modeled as a function of t. So the key theorem behind it is that the curve t equals t and f of t can partition the space into several regions, and we are interested in the potential collision region. The leftmost point of that point, that region will be the earliest collision time. And for the polygonal case, we can decompose f of t into translational and a rotational component, and by solving an optimization problem, we can get the earliest collision time. And thank you for your attention, and I'm looking forward to see you in the active session for more details. Thank you.
Yeah, so hi everybody. My name is Andreas Hermann. I'm from the FZI in Karlsruhe, Germany, and I'm going to talk about my GPU-based voxel collision detection system. So in this video here, you see a typical situation for a mobile service robot. You have a dynamic environment, and the robot has to go from the left corner to the right corner. What you see here is its motion plan represented in form of a swept volume. So this is a safe corridor for the robot. As long as the robot moves inside this corridor, there's no collision. If a dynamic obstacle now intrudes this swept volume, the robot will stop, and it will trigger a replanning. So we are using a voxel representation here for the robot as well as for the environment. It looks like this. You have two maps, one environment, one robot, and you can intersect these two maps, do a pairwise collision detection on the GPU, and what you get is the resulting set of colliding voxels. So this is very well suited for parallel calculations on the GPU, but the problem is that you have a dynamic environment, and therefore you need a dynamic size data structure on the GPU, and this contradicts somehow the programming paradigms of a GPU. So therefore we had to come up with a solution. This is our load-balanced octree, which has a custom memory management and some other impressive technical details, which are the speed that you can build up this octree on a GPU. You can insert up to 10 million voxels within 100 milliseconds into this octree, and this already includes the free space calculations on the GPU. So this enables us to use real-time map updates with multiple point cloud sensors like the Kinect. We also implemented very efficient collision checks that are able to check up to 100 million voxels in only 20 milliseconds, and this enables us to do online replanning and real-time execution monitoring. Last but not least, one nice thing with the voxel representation is that you can check whole swept volumes of trajectories in the same time that you would need to check only single poses of the robot. So based on that, we came up with a special swept volume planner, and the system also supports shared memory visualization of live data. So here you see the system in action on our reader robot. The robot comes up with a plan just straight through these obstacles, and now I'm placing a new obstacle there. The robot detects this and does an online replanning without stopping the robot. So it's very fast and very capable. And if you're interested in it, please go to gpuvoxels.org. The software is available open source, and see me later in the interactive talk. Thanks.
Hello, I am Charles Dabadi, and I'm going to present you the research paper I worked on at UC Berkeley. So the title is a practical reachability-based collision avoidance algorithm for sample data systems application to ground robots. So we'll first start with a motivation slide, so you get an idea what are the main goals of this project. So first, what we wanted to do was to solve the two-player collision avoidance game in a novel way using a reachability analysis. Also, we wanted to apply the solution to ground robots. Moreover, we wanted to take into account the sample data nature of the systems we are considering. Indeed, ground robots, such as many experimental platforms, have a controller and a state estimator that have a sampling period. And finally, we wanted to make the solution practical. The figure on the left is a picture of our experiment using the ground robots at the hybrid systems lab in Berkeley. And the figure on the right is a mathematical formulation of the two-player collision avoidance game. So now I will go through the main results we obtained. So we designed a collision avoidance algorithm that is based on reachable sets, and that is lightweight. Also, it deals with numerical approximations so that safety is preserved. It can easily be implemented on experimental platforms. And finally, it can be wrapped around any pre-existing controller in a synergistic fashion, using the concept of freedom set that I will explain more during the interactive session. On the video, there are two robots. The green one is using the collision avoidance algorithm, and the red one is remotely controlled so as to cause collision. So to solve the collision avoidance game, we needed to identify the set of initial states that may lead to collision over a one-time interval. So at every initial state, we fix the control input of the evader, which is called U, and we checked whether there existed a disturbance input for the post-war that leads to collision. If it is the case, it means that the initial state belongs to the backward reachable set of the avoid set A, which is synonym to collision. So this is what the mathematical formulation at the top of the slide means. So on the figure, the two sets of interest, which are the backward reachable set and the avoid set, are plotted. And if the initial state belongs to the backward reachable set, then the trajectory may end up entering the avoid set, while if it doesn't belong to the backward reachable set, you're sure that your system will remain safe over a one-time interval. I hope you found this interesting, and I will be very happy to talk to you more during the interactive session. Thank you for your time.
Hello, everybody. This is my topic, timescale collision cone-based trajectory optimization for reactive planning in dynamic environments. I'm Bharat Gopalakrishnan from IIIT Hyderabad, India. So the primary contributions of our paper are, we have an efficient method for computing intersection solution spaces for large number of predicted dynamic obstacles. And then after we do that, we have an optimization framework to connect our current state to the current state to the solution space in time optimal fashion. So what is the problem we have here? The problem we have here is that we have a robot over here, and we have to reach the goal in such a way that it satisfies a collision cone constraint, which is basically a differential constraint. So this differential constraint is given by this equation, which is nothing but the collision cone, and the robot's evolution model is highly nonlinear and complex. And here also, this equation also nonlinear and convex, I mean it's basically nonlinear. And the intersection of evolution model and this dynamic constraint forms a very nonlinear and a non-convex problem. So what is our solution? Our solution is basically divided into 3 steps. The first step is that we introduce a scale parameter in this differential constraint, and the entire collision cone constraint reduces to this, which is parameterized in terms of the scale, which we just put here. And this further reduces into a very simple quadratic inequation. Now finding the scale from this inequation is highly simple. So we end up finding the value of S, which we introduced here. Now the second step is, now this is the second step of a solution. The second step is that after we find the scale, we would like to generate different candidate trajectories. And we select the best candidate trajectory we select the best candidate trajectory by the simple cost metric, which we have defined over here. And if you see, there are 2 parameters associated in this cost metric. The second parameter over here is the cost associated for changing the path of the robot. And the first parameter over here is the cost for acceleration or deceleration. So based on this, we select the best candidate trajectories as shown in this figure over here. This is the third step. The third step is that now after we select the best candidate trajectory and evaluate the scale, we have to reach the scale velocity in minimal time. So for that, we parameterize the entire scale, which we had in the previous slides, in terms of sum of exponentials defined over here, Q1, Q2. And we evaluate the value of Q1, Q2 by minimizing an objective function, which ensures that we can reach the scale velocity in minimal time, and also it maximizes velocity. So for the videos, please come and meet me in the interactive session. Thank you.
Good morning. My name is Jan Lunenberg of the Eindhoven University of Technology, and I'm here to explain the work we've done on robot navigation in domestic environments. This is our robot Amigo driving through an Octomap representation of a scaled version of the 2013 RoboCup at-home environment. Now, we can do a down projection of all occupied cells, inflate that with a robot radius so that we know where the robot can and cannot go. I guess everybody knows this doesn't work in practice. There is uncertainty about the robot position. There is sensing uncertainty. There are obstacles moving through the environment. So usually, this cost map is inflated with some exponential function to take those uncertainties into account. However, this still does not lead to the desired behavior. If we inflate our cost map too much, the behavior becomes too conservative and the robot does not want to drive through narrow passages. On the other hand, if you don't inflate enough, behavior might become dangerous. Therefore, we have to try and model all uncertainties in our representation explicitly. Sensing uncertainty is the first thing. This is already addressed in the probabilistic integration of sensor measurements of the usual OctoMap framework. Usually, when no new measurements are received, the probability of cells being occupied remains the same. However, the environment might change in this time. Therefore, we added a time-dependent occupancy probability model. Furthermore, to account for moving obstacles that might come out of occluded parts of the environment, we inflate our probability cost map to make sure the robot doesn't bump into these obstacles. Finally, we model the robot position uncertainty using a bivariate normal distribution. By combining the probabilities of a cell being occupied by both an obstacle and the robot, we can compute a safe velocity limit for the robot. The result can be seen in this video. The robot will speed up as soon as it gets into the lighter gray area of the environment, but as it moves along, you will see that it slows down when it passes the first doorway to account for possible obstacles coming out of the doorway. Further on, it will slow down as well because it has to go through a narrow passage by itself. If you drop by during the interactive session, I'll be happy to show you more of this video and also explain the results that you can see on the bottom right graph in more detail. Thank you very much.
Hello to everybody. My name is Arne Hildebrand and I work, like my colleagues, at the Institute of Applied Mechanics at the Technical University of Munich. And I will present you today our work of the last year. It's named Real-Time 3D Collision Avoidance for Biped Robots. Our main motivation was to let our robot walk in unknown environments, detect obstacles, avoid them, while using the ability for biped robots to step over them. So at first, let me give you a short introduction to our general control scheme. It's an hierarchical-based scheme. We have, first of all, the step sequence plan and the walking pattern generation, which generate trajectories in task space. Then the reactive control, it's a stabilization unit, which is executed during the stepping of the robot. Now we added first obstacles to our self-collision avoidance method, which was presented in previous work. But it's not really, this work here is not really focused on this obstacle representation. Our method consists, first of all, of the step parameter adapter, which calculates valid foot step positions. So we don't want that the robot step on an obstacle. And the second part is this also calculate an initial solution for the swing foot trajectories using all degree of readings of the foot. So then it's the part of the reactive control. This part modifies during the execution of the swing foot movement the all degree of freedom of the swing foot to avoid the obstacles using a local potential field approach. So now I show you one video of our the experimental validation. In the right, you can see our collision model and the robot Lola, which walks over a triangle obstacle. So I hope you can see us at my poster session. Thank you for your attention.
Hi everyone, my name is Shishen Cai. The title of my work is Ensuring Safety of Human-Robot Coexistent Environment. The motivation of our work is very simple. We want to put a human worker and a robot together and cooperate with each other, and also avoid the robot to hit the human workers. So the contribution of our work is we design a measure for the safety of the human workers, and also we developed an algorithm for generate trajectory for robot to avoid collisions and also accomplish its task. So in this work, we use optimization-based trajectory planning. We also combine the absolute coordinate and absolute representation and the safety index, discrete kinematic model, and the receding horizon strategy. And later, we approximate this formulation into a quadratic form so we can compute it in real time and very fast. For the absolute representation, each of the human worker and the robot, we use a set of absolute to represent it. So this is an example of the human worker and the 7 degree of freedom of robot. In 2D case, it looked like this. And for the absolute of the robot, we further define an absolute coordinate, that is. So for every point in the text space, from this point to the absolute center, we can compute the absolute center. We can compute this short distance in this absolute coordinate, and it looks like this. And so we can compute the absolute in this absolute coordinate to the absolute center. And based on this short distance in the absolute coordinate, we define a distance safety index. We also use the linear momentum from the robot link to human to define a momentum safety index. And later, we combine these two together. For the formulation of the optimization, we consider two terms in the objective function. One is to drive the robot toward a goal position, and the second is to smooth the trajectory. And as I said, we use a discretized kinematic model to make sure it's the trajectory, not the path. And then we put a safety index in as a hard constraint to make sure the safety of the human workers. So this is a simulation result. We simulate in 2 degrees of freedom and 7 degrees of freedom. And the robot is always on the left-hand side. And as you can see that the robot can avoid the human in the real time. And actually, in not real time for the 7 degrees of freedom, but it's still very fast. And so, welcome to my interaction session for further detail. Thank you.
Hi, my name is Stella Tomic. I'm a researcher at the German Aerospace Center. And I'm going to present work done together with Sami Hadadin on a unified framework for external wrench estimation, interaction control, and collision reflexes for flying robots. For the motivation, well, autonomous flight in unknown cluttered environments requires exteroceptive sensors for collision avoidance, which may fail or be inaccurate. For example, due to sensor resolution, if the obstacle is too small, or due to environment reflectance properties, for example, a camera not seeing a window, or a laser scanner also seeing through a window. Therefore, flying in unknown environments may lead to unforeseen collisions, which may cause serious damage to the robot, as you can see from these videos. So in this context, fast and robust collision detection combined with safe reaction is essential. And this may be achieved using external wrench estimation. So in our paper, we use the control input, system model, and proprioceptive sensors to estimate the external wrench using a momentum and acceleration-based method. We use this wrench for interaction control because a collision is a physical interaction with the environment. And we also investigate collision reflexes. That means detection of the collision, classification, isolation, so the collision position, and safe reaction. The external wrench estimator requires only the IMU, and we estimate the external force using the accelerometer, so we don't need a translational velocity estimate. And we use the external torque using the angular velocity measurement. This can be used for impedance control. Our formulation allows inertia shaping, and we feed back the external wrench estimate. So here you can see the response for the same quadcopter with different virtual masses when the same load is applied. So we can shape the inertia of the system. For the collision detection signal, we use a threshold on the high-pass filtered external wrench estimate. And using the wrench information, we can also determine the collision position on the UAV's convex hull. We investigated several collision reflexes, and we showed that the method is very sensitive And if we react to the collision, the robot returns to a safe state and can be returned to a higher level planner. So to conclude, this method provides a safe collision reflex between collision avoidance and control. Thank you.
Hello. You all know the Microsoft Kinect sensor. It's cheap and provides depth maps at 30 frames per second. However, it's an active sensor, and as any other active sensing technology, this could cause interference. My name is Roberto, and today I'm going to present the results of our analysis of the measurement degradation due to the interference of multiple Kinect sensors. Imagine this scenario. And now imagine that each one of these robots would carry a Kinect sensor to perceive the world. So, well, the good news is that they couldn't see the good guy, Will Smith, because all of them would be blind. In our analysis, we focus in great detail on the interference between two Kinects, and we observe that up to 90% of the measurements are invalid due to interference. So this is a common scenario in robotics. Two sensors are pointed to the same surface. This could represent two robots looking for an object or collaborating for a manipulation. This video shows the infrared view of the patterns from both Kinects, and as you can see, they overlap. This is the area where the interference appears. These videos show the depth measurements obtained from a Kinect when the other Kinect is off on the left side and when an interferent Kinect is on the right side. You observe these black areas. These are measurement failures, pixels where the sensor cannot provide any depth measurement. And you also see that these failures appear naturally without interference, just because of the reflectance of the surface or because of shadows. But with interference, these measurements are more frequent. We measure these measurement failures caused by the interference, and here I show you just an important part of our results. In these plots, we show the fraction of the measurements that fail when one of the sensors is at 1 meter distance of the observed target, and a second sensor is moving between 0.5 meters and 1.5 meters of the same target. And you can see that up to 90% of the measurements are invalid due to the interference between the sensors. This can cause a failure of any or most of the applications based on Kinect sensors. If you want to see the complete results of our analysis, or you want to know more about our first analysis of the interference between multiple new Kinects, the Kinect 2, please come to my poster. Thank you.
Hello everybody, I am Pierre Mario from IRSM. My presentation today is about gangway automation for maintenance operation in offshore wind farm. Today there are two solutions to access to offshore wind farm turbine, but there are major safety problems. The first one, we go with a small boat, but we have to come in contact directly with the wind turbine pile, and the operator have to jump directly on the ladder. The second one, with a bigger boat equipped with a gangway, but this gangway have to securely attach to the pile. As a result, it is difficult to release quickly in case of emergency. So we propose to develop a compensated contactless gangway. Il vous manque un bout. Your system. The boat is equipped with a dynamic positioning system to maintain its position. But it's not able to compensate the 3 degrees of freedom, roll, pitch, and vertical movement called heave are not compensated. As a consequence, we need to control the 3 degrees of freedom and find a way to measure them. We use two types of sensors. An inertial measurement unit measure roll, pitch, and heave with good precision. We have evaluated them. And we use a LiDAR at the end of gangway as perception system to measure the 3 other degrees of freedom. So in this article, we propose a robust wind turbine pile detector in LiDAR scan. On the right figure, you can see a LiDAR scan. You can notice that there is only a few points come back to the LiDAR. This is a four-step algorithm to estimate the position of the pile. The first step is to, with the EMU, we project the 3D point in the horizontal plane, in an horizontal plane. Then we use a Landsat to find the most likely circle. A circle fitting optimizes the best solution in all the points selected by the Landsat. And the noise generated by the LiDAR and other artifacts are filtered out by Kalman. On this short video, you can see the global simulation of your system. Use your pile detector. As you can notice, the end of the gangway is stationary in front of the wind turbine. But it's just simulation, and to validate your algorithm in your laboratory, in real world, we build a small-scale wind turbine pile and use a Kuka arm manipulator to reproduce the sea movement. If you want to see the result and have more information, please come to see me at the interactive session.
Hi, my name is Chris Jordan, and today I'll talk to you about the work I've done with Filipos Mordechai about quantifying the different methods of estimating normals in a point cloud. So the point clouds are becoming more prevalent today, and they're very useful in computing things such as shape descriptors, which are in turn useful in object recognition, terrain classification, and obstacle avoidance. These have to be done fast and they have to be done accurately. And so far, to our knowledge, there has been no quantitative study done with a ground truth on the different methods. So the methods we tested either fit a planar or a quadratic surface, and they focus on the effects of different parameters, such as normalizing the vectors used in computation, anchoring the points around the neighborhood mean or the reference point itself, adding weights to decrease the effect of the further away points, and adding noise to the point cloud. And we ran these methods on 40 different models provided by Dudugachi. So one of the methods we tested was plane PCA, and it fits a plane to the set of points. And it tries to find the direction of the minimum variance, which also is the normal to the fitted plane. And as you can see, the objective function looks like that. And then the different modifications we had, we show them on the plane PCA method. So here we normalize all the vectors used in the computation versus not normalizing them. We have the anchor selector around the neighborhood mean versus the point itself. And we add Gaussian weights to decrease the influence of further waypoints. From our computations, we have found that the use of the reference point is detrimental as the noise increases. We found that normalization is beneficial, and we found that using weights is detrimental when the neighborhood mean is used as an anchor, but it's improved when the reference point is used as an anchor. I want to thank you for your time, and if you have any further questions, please see me during the interactive session. Thank you.
Hi, my name is Sylvain Vasquez, and this is part of my PhD thesis. I am working with Enrique Zúcar and Rafael Murrieta from Mexico, and this work is deep learning for 3D object reconstruction with a mobile manipulator robot. 3D models from real objects have several applications in robotics, such as manipulation or motion planning, and to build this model, several views are required. With a view, I mean the sensor pose and the robot configuration. Given that the object is not known in advance, each view is planned iteratively, one by one. And this is the algorithm to reconstruct an object, and we are dealing only with the next best view planning. Usually, the next best view is computed first by the sensor pose, and then by means of inverse kinematics, the robot configuration is computed. The proposed method computes directly the robot configuration, and it the trajectory. And this method is based on a sampling of the configuration space and a fast evaluation and rejection of the samples with a utility function. The utility function that we propose evaluates several aspects of a desirable next best view. And given to evaluate a large set of views could be very expensive, we propose an evaluation strategy where the utility function is implemented as a series of factors. We did experiments in simulation and with a real robot manipulator with 8 degrees of freedoms. We did a comparison versus the information gain approach in the reconstruction of several complex objects. The results shows that the utility function reaches the same coverage that the information gain approach and with a higher coverage of the objects. In conclusion, our experiment shows that it is possible to plan the next best view directly in the configuration space using direct kinematics. For an 8 degrees of freedom robot, the processing time is in the order of seconds when we use the evaluation strategy. So I hope to see you in the interactive session.
Okay, hello. My name is Elder Araújo. I'm the second author, and I'll be talking about pose estimation in the case of a mobile robot moving on a plane. And to estimate this pose, we consider as reference or landmarks 3D lines. And as a model of the sensor, we use a generalized camera, which can be a central, non-central camera, or even a set of cameras that are considered together. So the problem is to estimate rigid transformation, which is basically one rotation and a translation. And in fact, in this specific case, this is a rotation of one angle and 2D translation vector. So what we have is the non-central camera, generalized camera calibrated, meaning that for each pixel we know the projecting line and we know the coordinates of 3D lines. These 3D lines are projected as lines or segmented lines onto the image, and from these projections we compute the rotation and this translation. For that purpose, we use the condition that if we express two lines in Plucker coordinates, there is a condition that expresses their intersection, and from this polynomial equation, we, since these both lines, meaning the projecting line and 3D line, they must be expressed in the same coordinate system, we introduce the rigid transformation, and this rigid transformation allows us to compute the pose of the robot in the world relative to the camera system. So this is expressed as optimization problem subject to constraints, and these constraints basically they restrict the kind of motion that the robot can perform, in this case planar motion. And by restraining or constraining the solution, we basically are able to achieve a robust estimate for pose, and which is actually quite robust also against noise. And so we basically use 4 lines, and the minimum would be 3 lines. And in some, if you allow multiple solutions, even 2 lines. So with 4 lines, we're able to robustly estimate the motion of the robot, pose, and of course also the motion. And if you want to see some more details, please show up at the interaction session. Thank you.
Good morning, everyone. My name is Yoann Dupuis. I'm a research engineer at CEREMA, a French governmental agency. It's my pleasure to introduce you to the work we've done with my colleagues from IRSIM and LITSIS back in France. The topic of my talk will be GPS-based preliminary map estimation for autonomous vehicle mission preparations. So let's first see the motivation of this work. Road maps are really important for autonomous vehicle navigation.
They are used in multiple tasks such as path planning or localization. But while road maps are really accurate in urban areas and big cities, they may be outdated or incomplete in countryside or suburban areas. And even if you are a really good localization algorithm, like the paper presented on the right-hand side of the slide, if your map is not accurate, you may face two situations. First, your algorithm may never converge, and you never get localized, or you were localized and you get lost. So there exists several work on estimating road map from multiple GPS traces. But most of them use a lot of GPS traces collected from commercially tracked vehicles. They also requires a lot of time to compute the map in case of the update. So what we want to propose is to estimate a map from crowdsourced GPS traces gathered from low-cost devices. And this work has to be done from only a few GPS traces. So in order to do that, we use a spline-based representation of the road. Then we use the control points of the spline in a state space representation and a Kalman filter to ensure an easy and fast update of the road map. In order to evaluate our approach, we collected different GPS traces from different drivers, vehicles, and time. We evaluated our approach against an only one INS GPS data, and we compare our result with commercially freely available digital maps such as Google Map and OpenStreetMap. So our result shows two things. First, we achieve a fast computation in case of map update, or if you want to obtain a brand new map without prior knowledge of any governmental data. Our second result is, let's say, a good performance. On the right-hand side, we compare the map we obtain only from few GPS traces to Google Maps data and OpenStreetMap data. And as you can notice, in some part of our work, we are able to outperform this data. So we ensure a good quality. Thank you very much for your time.
So my name is Zhan Liu. I come from the University of Tübingen. So the paper I'm going to talk about is dynamic object tracking with a mobile robot using passive UHF RFID tags. So this is a joint work together with my colleagues, Goran Hviskic and Andres Sev. So we are interested in passive RFID tags, which works at the ultra-high frequency band. So these tags can be detected up to some 7 meters. Also, they do not need a battery. Basically, they're very small. They can be placed on the products. As you can see here, on the left image is a supermarket environment. Also, these tags can also be placed, for example, on the books. But we are interested in tracking dynamic RFID tags. As you can see here, is a person carrying an RFID tag, and the robot is trying to follow this person and keep some distance between the robot and the person. And now I'm going to show you a video of our approach. You can see here, our robot has 2 RFID antennas. So these antennas are able to measure the signal strength. With this signal strength, the robot knows where is the tag. And with the position of the tag, the robot is able to follow the person and also keep some distance between the robot and the person. You can see the environment here is our supermarket environment. In the supermarket, we have around 500 RFID tags. So if the signal strength is higher than threshold, the robot will stop. And here is another example. The robot is following a person in a corridor environment. Also, the robot is able to go into the elevator and get out of the elevator. So we are quite surprised by this because basically the elevator is made of metal, and the metal has a very high influence on the detection of RFID tags. And now you can see another example. The robot is following a person in a very narrow corridor in a library environment. So in our library, we have around 5,000 of books with RFID tags. And this environment is also very challenging because the performance of RFID reader highly depends on the tag densities. More precisely, the approach we use is based on particle filter. So to deal with motion uncertainty, we use two-stage dynamic motion model to recover from the tracking failures. Also, we use a dual particle filter to recover from tracking failures. So for more information, you can come to the interactive session in the afternoon. Thank you very much.
Good afternoon. The problem we're addressing here is detecting moving objects, specifically pedestrians and vehicles, as seen from a camera mounted on an autonomous vehicle. I'm the third author, Marcelo. I'm with the National University of Singapore. This project is supported by SMART, the Singapore MIT Alliance for Research and Technology. It's part of a program on future transportation, future urban mobility. So tracking moving objects is a seemingly very simple idea. If we can know the relative velocity of the moving object relative to the car, and since the car has sensors, we know the velocity of the car, right? But we can improve much more the performance, the detection accuracy, and tracking accuracy if we introduce additional features. And what are these additional features? The first is we will use what we call the space-time point cloud. It's 3D. XY is the XY position, and the vertical axis is the time domain. And here it detects, in figure A, it detects 3 moving objects. These are moving pedestrians. They're bounded by purple boxes. The green is the past time. The red is more current time. And in B, this would be a moving vehicle. And on the right side here, the purple arrows here are the results of the velocity directions and of the different objects obtained. So we extract the point cloud, this 3D point cloud, we extract the surface normals, and this slide shows how we do it. This will be, for example, in the XY plane as the vehicle is moving. Here we have the delta X, delta Y, and delta T in the vertical plane. And if there's a slope, like here there's a slope, it's moving, but if it's vertical here, that means there's no change in position over time. That means it's a static object. So we extract the normal, expressed here, with the components nx, ny, and t. From here, we will have the velocity information. And we also find the shape, which is the spatial temporal shape, using the eigenvalues. That's the second feature. The third feature is the noise, and then the number of neighbors around each scan point, the distance, and the orientation error. So here are some results of that. We use SVM classification. This is moving, the vehicle moving in the evening in our university town environment. You can see the moving objects, the pedestrians being tracked in real time. And we track it using common filter tracking. The data is trained using SVM offline, but the actual implementation is done in real time after the SVM has been trained offline. So I'll see you in Saloon 12 after lunch. Thank you very much.
Hi everyone, my name is Nargis and I'm working with Professor Volkan Isler in the Robotics Sensor Network Lab at the University of Minnesota. And today I'm going to present our work on the role of target modeling in designing search strategies, which was done with Dr. Renzaglia. So the main motivation of this work is our ongoing project on invasive carp monitoring in Minnesota lakes. The invasive carp are a huge threat to the health of the lake because of their bottom-feeding behavior, which pollutes the water. And to track and trap them, some of them are being radio tagged that emit signals that can be detected by a directional sensor. And in our lab, we have developed a robotic autonomous surface vehicle system that can move around in the lake and look for the radio tags. So the search problem here is to find the fish. The fish is our target, and our ASV is our searcher. But before designing search strategies, we must first decide on the model for the motion of the target. On one extreme, we can assume that the target is not moving and it's stationary. In this case, the search problem becomes a coverage problem. And on the other hand, we can assume that the target is moving, but it's adversarial, in which case the problem becomes a pursuit evasion problem, which I have presented our recent result yesterday. In between these two extreme cases, we can model the target as a stochastic process. For example, we can assume that the target is doing a random walk. And this is what we have studied starting from last year. We assume that the target is a one-dimensional random walk moving along a line. And in this paper, we study search strategies to find a random walk moving in a two-dimensional environment, a square region, for example. And one might think that coverage strategies would work here because the target is randomly moving in the environment, but this is not true because the searcher is also moving, and so it can exploit its motion to update its belief about the location of the target in the environment. In this work, we provide insights about different search strategies that can give us better results. And I would be happy to present these strategies in my interactive session. Thank you.
Hey, good afternoon. So this talk is going to be centered around a gripper inspired by gecko feet. Geckos have nano and microscopic structures on their feet that allows them to adhere to a variety of surfaces, and we've replicated this in a polymer. The adhesive is insensitive to temperature, pressure, radiation, works over tens of thousands of cycles, and adheres to a variety of spacecraft surfaces. So as the shear force is applied to these stalks, the structures flip over, and the contact area between the gripper and the object increases by orders of magnitude. So what's the problem that we're trying to solve? So basically, the better your gripper is, the less demanding the control system managing it needs to be. So if you do not rapidly attach to a surface in space, you or the object will tip off due to the reaction forces. In the same vein, you want to know that you've got a good grip on an object before you exert any forces yourself. So the idea is the last thing you want is your $1 million inspection robot floating off the space station. So we've crafted a device that can rapidly actuate and also can gauge the quality of the grip. So really what we're after is we want to know if the pad's engaged or not. Am I adhered? There's some required preloading that's necessary, so you also want to know the amount of normal force. And when do I need to actuate? How far away is the object? Really, we were after this, but because of the design of the device, we found out we could extract those data as well. So here's a quick video that shows the rapid actuation. So we'll go through normal speed, slow it down, higher frame rate, and then regular speed. So the stocks themselves we speculate that they can actuate much, much faster than this, but due to the camera limitation, we could kind of tell it's about 16 milliseconds. So. All right, so the sensor system has IR emitters and detectors underneath the skin. So here's the device itself. So this is the gecko adhesive, and underneath that is a printed circuit board with the emitters and detectors. So what we're sensing is the amount of light being bounced back from either the object or the gecko adhesive when it engages. So here it's unengaged, here it's engaged, and when those stalks flop over, they create a frustrating light path that scatters much of the IR beams back to the detectors, and you can very easily discriminate these two states. So, and lastly, here's a busy, unreadable slide that I would be very happy to explain at the interactive session, but I wanted to show something that, hey, this is real data. So operating in proximity mode and contact mode, and us using a classifier to discriminate whether the pads have engaged properly or not. And with that, I hope to see you after lunch.